Hello, we're now going to work on questions 7.4, which is further questions on moments, this time also including support force questions and couples or talk. And question 1 says a uniform meter rule of weight 1.2 newtons rests horizontally on two knife edges at the 100mm mark and the 800mm mark. Sketch the arrangement and calculate the support force on the rule due to each knife edge. Okay, so one, we've got a rule which has a mass to it, so I tend to draw it with some kind of thickness. Assuming the rule has evenly distributed mass, then the centre of mass will be 50 centimetres, and that's 1.2 newtons. It's supported by a knife edge X and a knife edge Y, and the distances, the distance you can add in, okay, so the distance from X to the centre, well, X is 0.1 metres in, and this is at 50, so this must be 0.4. This Y here is at 0.8, this is 0.5, so this must be 0.3. And then the distance between the two, which we also need for these kind of questions, well, it's 0.8 minus 0.1, 0.7. Now, how do we work this out? Well, we say that the support force felt at Y, so SY, will be equal to W, well, you might call it W0 in this case because it's the mass of the ruler, but obviously if there was a weight, it would be that, times dx over big D. Let's look at these terms. W0, well, that's going to be equal to 1.2 newtons, it's the mass of the ruler. Dx is the distance from X to the fulcrum, or sorry, distance from X to the mass, which will be 0.4, so metres. There'll also be a dy, which we'll come across in a minute, and that will be the distance from Y to the mass, which will be 0.3 metres. And then capital D is the distance between the 2 points, which will be 0.7 metres. Substituting in here, we get 1.2 times 0.4 over 0.7, which calculates through to be 0.7 newtons. And then we can do Sx, which is equal to 0 dy over d, which in this case will be 1.2 times 0.3 over 0.7, which will equal 0.5 newtons. We can check that 0.7 add 0.5 adds together to be 1.2, which is the mass of the ruler, so it's completely taken up by the support forces. That's question 1 answered. Question 2. Question 2 has a diagram associated with it, so I'll show you that. If we can pick it up on the camera, it's this one. And it says that a uniform beam of weight 230 newtons and a length of 10 metres rests horizontally on the tops of two brick walls, 8.5 metres apart, such that the length of 1 metre projects beyond one wall and 0.5 metres projects beyond the other wall. Calculate the support force on each beam and the force of the beam on each wall. So, I know there is a diagram, but we'll just quickly draw it back out in simplified terms. We have a beam it's supported by 2 brick walls or brick columns. Now, convention says that we should draw square supporting columns, but well, that's it. We'll draw it and then we'll have a look at it. So we could draw the brick wall like this, and then this one, which is slightly closer to the edge on this side. Okay. In reality, though, we're going to consider the force of this, supporting force of this, to act for its centre, and this one. Okay. So theoretically, there was actually no need to have drawn squares. We could have just drawn knife edges still, although we know it's not a knife edge like it was here. At the same time, it will still act for a point, so it doesn't make actually a huge difference to us either way. It says that the distance between these 2 beams, and this distance given, it is shown on the diagram, is actually the distance between the centre points, not between the inner sides. Probably haven't drawn that brilliantly there, so that should be to the centre point. That distance is 8.5 metres, and then we have a bit of beam here, which is 0.5 metres, and a bit of beam here, which is 1 metre. It also says that the weight of the beam, which is 10 metres long, and therefore its mass, assuming it's universally distributed, will be at the centre. That mass is 230 newtons. So I like to add in the values that I need rather than the values it's given. I actually want these internal distances here. If it's 10 metres long, then take away 1 metre, this is going to be, well, first this is 5, take away 1, this is 4, and then this side, this is take away a half, so it's 4.5. So there's a diagram drawn out. Doesn't ask for a diagram in this case, but let's get used to drawing them. And then we can write a shopping list, if you were. We've got a weight of 230 newtons, distance between the 2 points of 8.5 metres, and then our internal distances, dx and dy. So dx is from the mass to x, which is 4, and dy 4.5. Now all the bits we need to make our calculations. So we can say, move this so it's still on the screen, Sy will be WO dx over d. Note the point that when I look at y, I use x. When I look at x, I use y. That's the only bit that we really need to consider. WO 230 times dx 4 divided by d 0.5, and we get an answer of 108 newtons. And then Sx is W0 dy, so it's the opposite, over d, 230 times 4.5 over 8.5, which works out to 122 newtons. The second part of the question says the force of the beam on each wall. So that's the support force that we've calculated. Let's draw that on. That's Sx, Sy. That's the forces we've just calculated. Well, the beam isn't moving, which means it's in equilibrium, which means whatever force we're pushing up with must be counterbalanced by the force going down. And therefore, the answer to question B is they're exactly equal and opposite. So you would have a force of 108 newtons and 122 newtons, but in the opposite direction. That answers question 2. Question 3. another question where we've got a diagram. So let's try and bring this up to the screen. We've got our lorry on a bridge of some description, and it reads that a uniform bridge span of weight 1200 kilonewtons and of length 17 meters rests on a support of width 1 meter at either end. A stationary lorry of weight 60 kilonewtons is the only object on the bridge. Its centre of mass is 3 meters from the centre of the bridge. I want you to calculate the support force on the bridge at each end. So we need to draw a diagram again here. We have our bridge, our span. Okay, that's supported by supports that are 1 meter wide at each end, and they sit directly under the end. This we can get from the diagram. And we have a weight of the span, which we call W0. This time we have a new part, if you will, of a weight here of the lorry, which we'll just call W. So W and W0 in this case. The next things we have to consider are distances. The internal distance between here and here is 15 meters, but as we talked about in previous, we have to consider where the force will act through. It'll actually act through the center of these columns. So through there and through there. So this is going to, if we call this X and this the Y end, this will be SX and this will be SY. Now when we look at them, if the gap between here and here is 15 meters, then the gap between the center point here and the center point here must be 16 meters, because these columns are 1 meter wide each. So we've got half a meter to the center there, half a meter to the center there. So the distance between the two, if we draw it from the lines, and it makes it nice and clear what we're drawing, is 16 meters. It says that the distance in this gap here, I'm going to draw it in with a red pen just because it's better at getting in the little gaps. The distance here between these 2 points is given to us as 3 meters, and that's how far from the center point the lorry is. We can also, let's pick out other things we can get from the question. We can say that the weight of the bridge, start building our shopping list at the same time, is 1200 kilonewtons. The weight of the lorry is given as 60 kilonewtons. We've now calculated D, which is 16 meters. Now, what do we have left to calculate? Well, we have to consider 2 masses this time. So we're going to have 2 values for distance and 2 values for mass. So when we have dx, we'll be looking at the value for the distance between here and here, and separately the distance between here and here. And then dy, here and here, and separately here and here. So the best way to add these on, in my opinion in that case, is work out the distances between them all and then add up the bits you need. So I'll draw some lines in here, draw these in here. Okay, now the distance from here to here is going to be, well, this distance is from there to there is 8. Okay, in fact that's this one, so we'll add that one in. So from here to here is half the span, which is that, so that's 8, which means this total distance here must be 8, but this has lost 3, so it's 5, and here's the extra 3 that we drew underneath. Now we have all the numbers in the question converted from what was given partly in the text and partly in the diagram to answer the question. Okay, now we'll call the distance to the weight 1 and the distance to the mass 0. So we're going to have dx1, which is a distance to the weight, which will be 5 meters, and we're going to have dx0, which is the distance to the centre of mass, which is going to be 8 meters. Filling in the bits we've got our y values as well. So our y value to the weight is going to be 8 plus 3, so it's going to be 11 meters, and to the mass 8 meters. These should be the same because we know it's halfway. Now I know theoretically I could read these off as I go along, but I like to build my shopping list. I like to know everything I need to know is now written here. I now can almost completely ignore this and just work from my shopping list. This is stage 1. It builds for me this stage 2 to move on to stage 3. And for a question like this, where it's a little bit complicated because you've got several variables at once, you've got to try and be methodical like that. So now we've got to calculate SY. Now we're going to take the first moment. So in this case we'll take the first one we're going to worry about to be the weight of the car. So that will be W dx1 plus the moment that comes from the mass of the span, which will be W0 dx0. I suppose for argument's sake we could call this W1, it just makes it all a bit neater. There we go. Now we still have to divide that by the distance between the span. Okay, when we put the values in for this, we're going to end up with, we can ignore the k's as long as we put the k's back in at the end, because we're not timesing k's together. We're only ever timesing k by a number, but if you wanted to, you could do it. It's up to you. It's risky unless you specifically know when, and when you can't ignore the k's or the times 1,000. I would always leave them in, but if you're confident with it, you can take them out. It will work fine taking them out as long as you remember that it carries through. We get 60 times 5 in the first brackets. In the second bracket we get 1200 times 8. I think I'm going to fit this in, but we'll write a little. 1200 times 8 over the distance between the two, which is 16, and when we calculate that we're going to get an answer of 619, and then remember to put the k back in, kilonewtons. And I wouldn't leave it in that sense. I would probably say that's 620 kilonewtons. When you're talking about kilo, then you would go to about 2 significant figures, something like that. And then SX, same system as before. This would be W1 dy1 plus W0 dy0. As you can see, I don't have to think about this. I can just write it just by changing x to y's, and then I just look for the bit I need. I've done all the confusing bits earlier on. I don't have to be confused whilst doing the maths, and it's best to keep the confusing bit separate from the maths bit. It avoids making simple maths errors where your mind or your attention is distracted. we're going to end up with 60 times dy1, which is 11, plus 1200, I wrote nice and big this time because we couldn't properly see this one, 1200 times y0, which is 8 over 16. These are actually killer, I'm just going to carry it through, and we get an answer of 641 kilonewtons, which again will give to two significant figures, the 640 kilonewtons. Okay, question 4. Just get a new bit of paper. Question 4 says a uniform plank of weight 150 newtons and length 4 metres rests horizontally on 2 bricks. One of the bricks is at the end of the plank, the other brick is 1 metre from the other end of the plank. Sketch the arrangement and calculate the support force of the plank from each brick. Then there's a second part of the question which involves changing it slightly, so we'll leave that for a second and come back to it. So, let's draw ourselves a diagram. We have our beam, as we're always going to have in these. The X end we can consider to be supported by a brick right on the end, we'll call that X. This end, the brick's not right at the end, we call this Y. The beam has uniformly distributed mass and therefore a weight at the centre of mass in the middle there. We can add in some values here. We're given, I'll put these in red because it's easy to see. We're not given the width of the bricks. It doesn't say that it acts on a knife edge, it just says that it acts on bricks. We're not given the width of the bricks. In this situation, we'll therefore take the distance to be the distance is given. We won't allow for the thickness of the brick. We'll assume it to be of no real thickness. So we'll take values, we'll take our SX to be acting here at the end of it, and SY to be acting here. Obviously, if it says to you in the question that these are 1 metre wide, or 10 centimetres wide, then they're looking for you to take it from the centre of the bricks, which we should be doing here, but we're given the question and the details we're given, we'll work to that as best we can. The distance from the centre of mass to this side is 2 metres, and the distance here 1 metre, because the overall distance is 4 metres, and it says that this is to the end and this is 1 metre in, so I've not drawn it very well, but that's also 1 metre there. So, building up our shopping list then, we need a distance D, which will be 3 metres, so we'll say D is 3 metres. Our distance from X to the centre, dx, is 2 metres, our dy is 1 metre, and our W0 is 150 newtons, as given in the question. Now we do our maths. Sy is equal to W0 dx over dy, so I use x, 150 times 2 over 3, which is equal to 100 newtons. And then Sx is our mass times our y value over d, which is 150 times 1 over 3, which is 50 newtons. Our simple maths, simple numbers there. Right, now then read on part B. A child stands on the free end of the plank and just causes the other end to lift off its support. Sketch the arrangement and calculate the weight of the child. Now, this has actually turned this question from one thing into a slightly different thing altogether. So we're actually going to redraw the diagram now. Now, if you're standing on the free end, we're assuming that means this end, because this is the overlapping end, and it's lifting ever so slightly just off of this. We're at the point where it just starts to lift off this end. X is now gone. As far as we're concerned, for our calculations, X is no longer there because it's lifted slightly off it. We can remove it from consideration. We still have the mass of the plank, and we still have Y. But Y in this case now is going to act like a pivot, so I'm going to draw it in as a fulcrum. We'll call that Y. And now, instead, we're going to have an extra mass or weight of the child, which I'll put in as W here. We need to consider the distances here. Well, we know that from up here, this is 1 and this is 1. And therefore, we don't actually have to do any calculation. We know that if the child is pushing down with a clockwise force, clockwise moment created here from the force W times the distance 1, it must be counteracted because it's balancing still. It's lifted ever so slightly, but it's not turning. We're considering it to be balanced by this anti-clockwise force of the weight of the plank times 1. So it means WO times 1 is equal to W times 1, which means WO is equal to W, which means the weight of the child is equal to 150 newtons. So no calculations, just a little bit of considering what's happening and how the questions change from what is a forces up and forces down situation into a moments around a point situation. And that is the end of summary question 7.4.